Hello, in this video we are going to derive the moments of inertia of multiple objects. The first one is going to be a thin rod of uniform mass and length L. So I have a thin rod, I have a mass M, length L, so the center of mass will be at L over 2. So that's going to be L over 2, and this is going to be L over 2. And since we have uniform mass, so it means the linear mass density lambda is going to be equal to m over l. Our equation from the previous video, it's I equals integral of r squared dm. We want to find what is dm. We are going to find it from lambda equals to m over l. So in that case, m is going to be equal to lambda times L. So dm, the change of the mass, is going to be equal to lambda times dl. We are going to replace lambda since it's a constant by m over L. So dm will be equals to m over L dl. Now I'm going to replace that in our original equation. So our equation is going to be I equals integral of r squared times m over L dl. And the boundaries of the integral, they are going to be from minus L over 2 to L over 2. Now, this r is going to be the what we are going to change. So that will be I equals minus L over 2 to L over 2 of m L squared dl over L. When we do this integral, when we integrate, we will get m L cube over 3L squared from minus L over 2 to L over 2. Right now, when we replace L over 2 and minus L over 2, we are going to get m L squared over 12. Okay, right now we are going to go over the thin rod at the edge. So thin rod at the edge. This is the one that we derived using the parallel axis theorem. So again, it's going to be a thin rod of mass m, length L, and uniform mass density lambda equals to m over L. But I want to find I from here. So it's going to be from 0 to L. We are going to get the same integral. I equals to from 0 to L of m L squared over L dl. By applying the integral, we will get m L cube over 3L from 0 to L, this small l, so it's going to be m L squared over 3. The third one is if I have a thin cylindrical shell, or it can be a ring. It means it's going to be empty from inside. It's going to just look like that. In that case, the mass is at the surface. So it's empty from inside. All the mass is just around the circumference. In that case, I equals, that's the simplest, as before, r squared dm. But since the mass is only on the outer surface, as I go from the center to the surface or to the edge, we don't have any mass. So everything is going to be outside. It will be integral r squared dm, which is going to be mr squared because the integral of the m is the total mass. The last one that we are going to derive is for a disk. Again, the disk, it means it's going to be a filled one. That's similar to when we have a pulley, or that's going to be like a filled cylinder, or you can see it as a solid cylinder. They are all the same. So I have one similar to the one above, but it is filled from inside. So it's a solid. Again, it's going to have a radius or mass m, and it's going to be a uniform mass. So I have a uniform mass density. In that case, we'll call it the sigma. Or we can know from this one that sigma is equals to the mass over the area. So the mass is equal to A, the area multiplied by sigma. So dm is equal to, the area is pi r squared. So the area is going to be pi r sigma dr. You learned that from calculus. So dm is going to be equal to pi r mass over area. That's what we replace sigma dr. And the area, as we said, it's going to be pi r squared. So when we do, we can simplify this one if you want, or we can keep it as it is. If you want to simplify it, dm is going to be equal to pi rm over pi r squared dr. The pi's they cancel. Dm equals to m r dr over r square. Right now, again, the I equals to integral of r squared dm, which will be integral of r squared, and instead of dm, it's going to be m r dr over r squared, and here we have to integrate it from 0 to r. So I equals to m r cube dr over r squared from 0 to r. When we do that integral, it's going to be m r to the power of 4 over 4r squared, which will be equal to m r squared over 2. So I of the disk is the half mr squared. That would be it for the derivations of the moments of inertia for different objects.